So I just finished teaching a topology class, and when we were going over metric spaces and the metric topology, I came across like an interesting construction example, which I thought was interesting, and I'd make a video about it. But let's recall what a metric is, as well as some things we looked at in a previous video where we looked at metrics. So we want to start with the set A, and then a metric will be a function D from A cross A to R. And maybe in very simple terms, the metric is like a measuring device or a ruler to measure distances between elements of A. And so as such, the distance should always be non-negative. You shouldn't be able to get a negative distance. And that's this first condition. So the distance between A and B is bigger than or equal to 0. Furthermore, the only things that should be distance 0 from each other are the same point. So in other words, the distance from A to B is 0 if and only if A is equal to B. Then you should get the same distance regardless of if you measure from A to B or from B to A. In other words, there's some symmetric property. And so that D of AB must be equal to D of BA. And then furthermore, you need something called the triangle inequality, which is maybe exhibited by this picture. So if you measure directly between 2 points, like in this case between A and C, that should give you something less than or equal to measuring between an intermediate point. So in this case, that intermediate point is B. Okay, so in that previous video, we looked at 3 metrics. The Euclidean metric, which is the standard way of measuring distances between points. And so recall that that's just built off of the distance formula that you probably learned like in high school. And what we get out of that is that the unit disk, well, it looks like a filled in circle. And I guess I should say these are all metrics on R2. They measure distances between 2 points in the plane. And as an illustration, I'll look at the unit disks or the points that are within 1 unit from the origin. Then the other metric we looked at is something called the taxicab metric. And that's given by the distance between points A, B, and C, D is the absolute value of A minus C plus the absolute value of B minus D. And that gave us unit disks of the following shape. So it's like a square on its side. Then there was this maximum metric, and that gave the distance between A, B, and C, D to be the maximum of the absolute value of A minus C and B minus D. Okay, so now that we've recalled that, I want to look at our new family of metrics that will lead us to some interesting, contradictory results. So members of this new family of metrics that I learned about are built from injective functions. Recall that an injective function is a function that's one-to-one. We'll see the definition of that during our proof. And so here we'll restrict our eyes to the real numbers, although I think you could do this on an arbitrary metric space. So let's say we've got a function from R to R, it's injective. Then we want to define a function which in essence goes from R cross R to R, so it's going to be our metric. And I'll write it as D sub f of AB. So this is a measurement of the distance between A and B, kind of with respect to f. And it's going to be the absolute value of f of A minus f of B. Okay, so let's start off by showing that this is in fact a metric. Okay, so let's notice that dfab, well, that's equal to the absolute value of f of A minus f of B. But the absolute value always gives us something that is bigger than or equal to 0. That's just because the absolute value is itself a metric. Okay, and so next let's notice that if we have dfab equals 0, then we know that the absolute value of f of A minus f of B equals 0. But that tells us that f of A equals f of B. And now we're going to use the important assumption over here that we have an injective function. But if we have an injective function, that immediately implies that A equals B. So we have that first condition of positivity, or really non-negativity, taken care of. And now we're ready to move on to the next condition, which is the symmetric condition. Okay, so let's look at that. We have d sub f of ab. So that's going to be absolute value of f of a minus f of b. But by the way that the absolute value behaves, we can simply flip the order of subtraction to get f of b minus f of a inside of that absolute value. But now that's exactly what we need it to be, namely it is df of ba. So this is symmetric. And now let's check that we indeed have the triangle inequality. So let's see, dfac, so that can be written as f of a minus f of c. And now what we'll do here is really a mathematician's favorite trick, which is to add 0 inside of this absolute value. So we'll add 0 in the form of f of b minus f of b. So let's put here minus f of b, then we'll put parentheses around those, and then we'll have plus f of b minus f of c. Great, so we just added 0. And now we're going to use the fact that the absolute value function indeed is a metric itself. And so it satisfies the triangle inequality. That allows us to split this up into the absolute value of f of a minus f of b plus the absolute value of f of b minus f of c. And now we're essentially done. We can just write down what those are in terms of our df function. So this is dfab plus dfbc as needed for that triangle inequality. Now, before we look at an example that I cooked up, I'd like to point out over here that this is any injective function. This function does not have to be well defined. In fact, this could be a seemingly very crazy injective function that mixes all of the points of the real numbers up in some sort of like seemingly random way. But regardless, you still get a metric. And once you have a metric, you can still talk about like open disks and things like that. Okay, so let's look at an example that I cooked up. So for our example, I'm going to restrict our setting to the interval from -1 to 1. Now, what we could really do is expand this to all real numbers and just have the function act as the identity off of this interval. But I think maybe all of the interesting stuff is happening right here in this example. So let's define f of x as follows. So it will be x if x is -1, 0, or 1. It's x minus 1 if x is on the interval from 0 to 1, and it's x plus 1 if x is on the interval from -1 to 0. So what effect does this have? Well, let's notice if we're on, like I said, this open interval from 0 to 1, so let's say, like I said, we're in that region, and we apply f, well, we get shifted back 1 unit. So we're shifted back here. So this magenta coloring denotes where we started and where we ended. And I'm going to put an arrow going in this direction and this direction to show that like the direction stayed the same. We were just like swapped over here. Okay, and then what's going on with this other bit? Well, if we start between -1 and 0, then we get shifted up to 0 to 1. So in other words, everything on this interval right here, you know, maybe thinking about it happening in this direction, is mapped to everything on this interval right here. So in essence, those two little sub-intervals are swapped. You know, their direction is not changed, but they are swapped. So now let's make the following important observation here. And that observation is that numbers that are normally close to 0 in our general setup for the real numbers are now pretty far away in terms of the interval from -1 to 1, of course, and then vice versa. So for instance, if we take the distance between 1/10 and 0, so maybe the f distance, I should say. So the normal distance between 1/10 and 0 is just 1/10. But in this calculation, it's different. So here we have the absolute value of 1 over 10 minus f of 0. So what's f of 1 over 10? Well, since 1 over 10 is between 0 and 1, we have to subtract 1 from it. Well, 1 over 10 minus 1 is negative 9 over 10. F of 0 is 0, so here we get the absolute value of negative 9 over 10, which is 9 over 10. So in fact, in this measurement, we have the number 1 over 10 is, fairly far away from 0. But then if we were to look at the f distance of 9 over 10 to 0, which usually would be pretty far away from 0 in this setup, we'll see that we get something fairly close. So here we get f of 9 over 10 minus f of 0. But that is going to be the absolute value of minus 1 over 10, which is 1 over 10. And that's really by the behavior of this map. So notice that 1 over 10 starts about right here, but when we apply the function, we get something right here. Of course, the point is really living inside of the normal interval. Its distance is just being calculated within the image. That's how this is like kind of going, if you will. And then let's maybe put another little example in here. So this 9 over 10, which is right here, is getting mapped to this negative 1 over 10, which is right here. Okay, so let's maybe look at an open disk of radius half centered at the origin to get an idea of what that looks like. So like I said, now we're going to look at an open disk centered at the origin. So this is like in parallel to what we looked at with our previously described metrics. So in other words, what I mean is all points x in negative 1 to 1 such that the distance, the f distance I should say, between x and 0 is, well, let's say the radius here is a half, so less than 1/2. So now let's notice in the normal distance, where we forget about the function and we just look at the absolute value of the two numbers, we clearly get something like this. But with our f distance, we'll get something different. So let's do that calculation. So notice that df of x comma 0 is equal to the absolute value of f of x minus f of 0. But that in turn is simply equal to the absolute value of f of x. And we wish for that to be less than 1/2 by our goal over here. But now let's notice that we need to split this into two cases based off of the fact that we have a piecewise defined function. Okay, so let's split that into two cases right here. Let's maybe in this case look at the case when x is bigger than 0. So that means we're in this zone. So that would give us the absolute value of x minus 1 is less than 1/2, which in turn gives us negative 1/2 is less than x minus 1 is less than 1/2. By the way, that an absolute value inequality turns into a compound inequality. But then that'll give us, let's see, 1/2 is less than x, which is less than 3/2. So it looks like x is between 1/2 and 3/2. Notice that x cannot get bigger than 1, so we have to cap it off at that. So that tells us that for this setup, we have x between 1/2 and 1. Okay, so now let's look at our other case. So for our other case, we have, let's see, x is less than 0. So that would be in this zone right here. So that's going to give us the absolute value of x plus 1/2 is less than 1/2. Again, pushing that to a compound inequality, we have negative 1/2 is less than x plus 1/2, which is less than half, which tells us we have negative 3/2 is less than x, which is less than negative 1/2. But again, since we're inside the interval from negative 1 to 0, we have to cut that off a little bit. And we'll see that that means that x comes from the interval negative 1 to negative 1/2. And you might say, well, okay, that's actually all the cases, but it's not. What if we have this secret third case when x is either equal to negative 1, 0, or 1? So let's write that here. So x is in the set negative 1, 0, or 1. Okay, but in that case, we have absolute value of f of x is less than 1/2, but f of x is simply equal to x here. So we have x in absolute values is less than 1/2, but among these 3 points, there's only one that satisfies that, so that is x equals 0. Okay, so let's put some boxes around these. So these are all the possibilities of points that are distance 1/2 from the origin. But let's put that all together and maybe write it like this. So this is technically written as the ball of radius 1/2 from the origin. That's just like a standard way of thinking about this. This is like a generalization of an open interval, if you will. And what we determined is that that is equal to the interval from -1 to 1/2 union the singleton 0 union the interval from 1/2 to 1 based off of all of those cases. But now if we wanted to, we could definitely graph that. So let's do that now. So this interval right here, so that goes from -1 to -1/2, so it's that portion. And then we have this singleton 0, which is this point right here. And then finally, we have something between 1/2 and 1, so we would have something like that. So I think that's a pretty interesting shape for an open disk centered at the origin. Okay, let's look at one more like weird example that can go on here. So we're going to finish this off by finding the limit as n goes to infinity of 1/n in this metric. So you might look at this and say, well, I know that limit, that's just 0. But that would be thinking inside of the normal metric, not the weird, strange like world that we're working in. So maybe we need a little bit of a definition, and this won't be a super proper definition, but some sort of defining idea for what we even mean by a limit here. Well, let's use this. Let's say that the limit as n goes to infinity of a sub n equals L if the limit as n goes to infinity of the f distance between a sub n and L is equal to 0. Okay, so let's maybe check if 0 is still the limit. And then, well, we'll see that 0 is not the limit, and then we'll find the actual limit. So let's look at the limit as n goes to infinity of the f distance between 1/n and 0. But let's see, that's the limit as n goes to infinity of, let's see, the absolute value of f of 1/n. But since 1/n is between 0 and 1, that will be 1/n minus 1. And then f of 0 is simply equal to 0. So that's all we have there. So we have something like this. But now notice as n goes to infinity, this 1/n term is going to 0, leaving us with the absolute value of -1, which is 1. So what does that tell us? That tells us that, in fact, the limit is not equal to 0 because the distance between the terms of our sequence and 0 did not go to 0. Okay, so now let's maybe look at our picture up here to get an idea for what it might be. Let's make an educated guess. So remember when we were drawing our picture before, this blue mark meant 1/10. And 1/10 seemed to be pretty close to -1, and that was like based off of what's happening in the image here. But now let's notice if we move this blue mark closer and closer to 0, its image will move closer and closer to -1. And since the function fixes -1, I think that's probably a good choice for us to test as the value of the limit. So is it -1? Okay, so let's look at the limit as n goes to infinity of this f distance between 1/n and -1. But then that'll give us the limit as n goes to infinity of, well, using our function up here, we'll see that we get 1/n minus 1 minus -1. Okay, but then that clearly simplifies to the limit as n approaches infinity of the absolute value of 1/n, which itself is 0. So that means that as n goes to infinity, the numbers 1 over n get closer and closer and closer to the number -1 in our metric. So that tells us that yes, in this specific setup, we have the limit as n goes to infinity of 1 over n equals -1. Which is a pretty strange happening. And now maybe a little bit of a story of how I came up with this. Well, like I said, I was teaching this topology class, and in class we covered it's inside of metric spaces. And we proved that if two metrics produced the same topology on a space, then in fact, sequences in those two metrics converged to the same points. But that really gave me this idea. Well, if we proved that with this condition about them creating the same topology, that must mean if you have metrics that don't produce the same topology, then perhaps they would have different limits. And then, well, I happened into this type of counterexample. And with this type of setup, you can really build like any type of limiting procedure you would like. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.